Hello everyone, this is Huanqi Cao from Tsinghua University. Today I'm here to share with you our experience on scaling graph traversal to 281 trillion edges with 40 million cores, which is on the newest generation Sunway supercomputer. First, let me brief on the task, which is the Graph 500 benchmark. This is the homepage website screenshot. It's a benchmark aiming at data-intensive workload, which is usually highly irregular and doesn't match the traditional supercomputer's architecture designed for physical simulation, etc. As is shown in its name, it has chosen graphs as its target data for its analytic workloads. Graph is commonly used and important data representation in data analysis, like social networks, web-link graphs, and so on. The graph data used in Graph 500 is an RMAT synthetic graph. It has a highly skewed degree distribution, simulating real-world small-world graphs. The benchmark then runs two kernels on it. One is breadth first search, the BFS, and the other is single source shortest path, the SSP. In this work, we target BFS as our task. This is the latest Graph 500 rank list on BFS. The scale parameter indicates the graph size it traversed. The GTAPs, which is giga-traversal edges per second, indicate the performance result. The first place now is Fugaku, which tackles a graph with 35 trillion edges and achieves about 100 teratypes. And the second place is our previous work on Sunway Taihu Light, which is also the predecessor of the machine this work used. And this is our result. 8 times on graph size, which is 281 trillion edges, 180 teratypes, which is nearly 2 times than the top, with an unprecedented scale of 40 million cores. The irregular workload of graph processing introduces multiple issues, including loading balance, vast communication, and so on. These issues ultimately result in poor scalability. The irregularity sources from mainly 2 points. One is the skewed degree distribution we have mentioned. This is a common feature of power law graphs, which occurs in both real-world data and the Graph 500 synthetic one. Some hub vertices may connect to billions of edges. The other is that edges in graph data may connect randomly far vertices, eliminating data locality and introducing heavy global communication when run on a supercomputer. As we all know, data partitioning is the very start of the scalability of a distributed algorithm. To tackle the scalability issue, we must revisit the partitioning methods, address issues, and solve them. The most simple solution coming to mind is to split vertices among nodes and access neighbors through interconnect. But with such partitioning, the aforementioned hub vertices comes in. One issue is the redundant communication, which sources from multiple edges pointing to vertices on the same node. Another one is load imbalance, which is because hub vertices have too many edges connected to them to process. Thus, it is not used at large scale nowadays. A commonly adopted optimization is to delegate the hub vertices among all nodes. The delegates are responsible to update its local neighbors. With such a modification, the edges on a hub vertices are divided to all machines into those orange local edges, resolving the load imbalance issue. Also, the communication required by the hub edges are replaced by communication between the hub and its delegates, eliminating redundant communication. It's a technique widely used in both general-purpose graph computing, for example Parallel, and the Graph 500 benchmark. This includes Ciccone and others' work on IBM Blue Gene series, and our previous work on Sunway Taihu Light by Heng Lin and others. The question then becomes adjusting the number of hubs. To think about it, we go through the benefits delegates bring to us. The first is to reduce communication. But if only so, only vertices with a degree larger than the node count should be delegated, resulting in the optimal hub number assigned to each node to be much smaller at extreme scale. The second one says it might not be. To eliminate load imbalance, heavy vertices causing imbalance must be delegated. But the number of heavy vertices also increases as the graph grows large. As an empirical result, we need constant percentage of hub vertices. Otherwise, load imbalance and other factors, including loss on early access potential in bottom-up iterations in BFS, will kill the performance. So we conclude a simple calculation. On Sunway Taihu Lite, we had 32,000 hubs per node, while each node had 27 million local vertices, which is about one hub in 1,000 vertices. When it grows to scale 44, our final setting, there would be about 17 billion hubs. Those hub vertices then cause 17 billion hub vertices to be maintained on each node, all requiring pre-iteration synchronization on their status. Obviously, it's not acceptable. Besides from the 1D based partitioning, there is also a partitioning based on 2D strategy that have achieved large scale. In this method, processes are first divided into a mesh. Then the edges are stored at its sources row and destinations column. The vertices data is first sent to the cross-point node through rows via a collective altogether. Then the cross-point node goes through the edges and combine the message into one. Finally, the edges get reduced on column via a collective reduce scatter, the result of which is used to update the destination vertices. This method on the Graph 500 list is mostly used by the Ueno team on K-Computer and Fugaku. While gaining similar benefits to degree-aware 1D partitioning, 2D partitioning also have similar issue on delegate count. It's equivalent to setting delegates for vertices on rows and columns, so that delegates count per node is approximately the local vertex count multiplied by square root of p, which is the processor count. In our case, it grows even further to 55 billion. Then the question becomes how to solve the issue on delegate count while retaining the benefits on communication and load imbalance. If we see from the 1D method, the problem is that with that much hub vertices, global delegates are created for those not so heavy vertices. Such vertices usually do not have that much edges to connect to most other nodes, which instead introduces redundant communication. On the other hand, if we see from the 2D method, it creates delegates for all vertices, even including those with very few edges connected. Those low-degree vertices better have no delegates to avoid redundant communication and maintenance work. We thus see a chance to combine the methods together. Up to this point, we introduce our new partitioning method, still called 3-level degree-aware 1.5D partitioning. The key principle is that the higher the vertex degree, the more delegates we create for them. We set 3 levels of vertex degree. The first one is E, which stands for extremely high degree. E vertices are delegated globally, similar to the hub vertices in degree-aware 1D partitioning. The second level is H, which stands for high degree vertices. Those vertices have a degree to cause load imbalance, but not yet worthy to be delegated globally. Thus, they are delegated only on columns and rows, similar to the vertices in 2D method. The third level is L, which stands for low degree vertices. They have only a few edges connected, thus we don't set delegates for them, and all its edges need to go through network. As a visualization, here we have a 3x3 process mesh 9 partitions in total. The blue vertex on upper left is a E vertex. The green vertices marked with 1 and 2 are edge vertices. The 9 purple vertices are different L vertices stored on different nodes. Before everything goes on, we first create delegates for the E and edge vertices. E vertices are delegated on all partitions. Edge vertices, instead, are delegated only on the same column and row of the original owner. L vertices remains there. The first set of edges are those connecting two E or edge vertices. For those vertices, we use the delegates to make them contact each other, just like in 2D partitioning. The edges thus become local edges on the column-row crosspoint connecting the two delegates. 2D partitioning does a pretty good job here to balance the edges among rows and columns. Also, it have a great chance to reduce communication, both at source sending and destination receiving. The second type is between E and L. As the owner of L always have a local delegate for the E vertex, we simply use a local edge to connect the E delegate and the L vertex. The benefits are pretty much the same as in degree-aware 1D partitioning. The third type is between edge and L. For those edges, the largest difference comes in. We use the delegate in the L's row to connect the edges. Once the edge vertices data is synchronized to the delegates are then responsible to contact the L vertices in its row. While it seems not reducing total communication, we notice that the network topology of large-scale supercomputers also have locality, or to say hierarchy. After mapping rows to the fast local network of the machine, we limit the remote edge communication to intra-row, reducing the communication across rows. The last one is edge connecting L vertices. Those vertices, those edges are simply made remote, except that we pack and forward the network messages through the column-row crosspoint. This message forwarding technique is inherited from our previous work on Sunway Taiko Light in order to better utilize the network bandwidth. And this is all for our partitioning method. After partitioning the graph into subgraphs, we have a chance to push direction optimization further. Direction optimization is a famous algorithmic optimization on BFS, which use bottom-up for dense iterations to reduce edge excesses. We observe that the dense iteration for hub vertices comes earlier than vertices with lower degrees. It's easy to imagine that it will be a lot easier for you to navigate to someone with 1 million followers than to a normal user like me on like Twitter or YouTube. As a quantitative measurement, the below figure shows the number of frontiers in different degree levels at each iteration in a graph 500 BFS run. Thus, we separate the direction choice of different subgraphs so that, for example, E and H can start bottom-up iterations earlier than L. But the heuristic for selecting direction needs to be adjusted. For those subgraphs with local edges, including EH and EH to EH, E to L, and L to E, we simply use source active ratio to select the direction. This is like in the original direction optimization, in which the heuristic is optimized for the possible early access. When the active ratio is significant enough, like over 1 in 32, there is a great chance that unvisited vertex will quickly find a parent and be settled. Instead, for those vertices with remote edges, we use source active ratio to estimate the percentage of forward edges to be fired as network messages and the destination active ratio for backward edges. Comparing the two ratios, we can have an approximation of which side will introduce fewer communication. We choose the economic side as the iteration direction to use. Then it comes to some architecture-related optimizations. Before diving into them, let me first brief over our platform, the newest generation Sunway supercomputer, which have a unique chip architecture. The processor, being the successor of the one used by Sunway Taihu Lite, is equipped with 6 MPEs as a full function cores and 6 accelerator core groups, each of which has 64 CPEs as accelerator cores. Each node have one such processor, 96 gigabytes of main memory. Each supernode has 256 nodes, mapping to a row in our 1.5D partitioning process mesh. The inherited key features from previous gen include the local data memory, LDM, and the direct memory access, DMA. The former is a manually maintained fast SRAM, and the second is a mechanism enabling fast coarse-grained copy between main memory and LDM. Fine-grained accesses to the main memory, while possible, remain slow on this processor. Also, several new features are introduced in this new chip. The two things relevant are remote memory access and local data cache. The RMA, as a new on-chip communication mechanism, replaces register communication and allows CPEs to access LDM of other cores in the same CG. The LD cache is a configurable cache sharing physical space with LDM and has no coherence guarantee. It's similar to L1 cache in CUDA architectures. So our first one is targeting EH2EH bottom-up, or to say pool. In EH2EH pool, which is the step visiting the most edges, random reads on column E and H vertices are required. Given that fine-grained DRAM load is slow on CPEs, and the E and H vertices do not fit into one core LDM, we need a mechanism to utilize LDM in this kernel. Thus, we introduce CG-aware core subgraph segmenting. We split the destination vertices into segments, such that each segment fits into the total LDM space of one CG. Given this, we can prefetch the segment into LDM cooperatively with the 64 CPEs. Then on each CPE, we use RMA to randomly access the in-segment vertices. This optimization is similar to NUMA-aware optimizations based on graph segmenting on CPU in Spirit. The other one is on-chip sorting with RMA, which is a fast CPE parallel bucket sort implementation on the new Sunway. We have designed two versions of on-chip sorting kernels on Sunway Taihu Lite, both based on the old register communication. On this new processor, based on its reworked intercore communication, the RMA mechanism, we also rework on the design of on-chip sorting. As RMA being a lot more flexible than the previous register communication, we simply use buffers combined with block-wise RMA between producers and consumers to form channels, and use these channels to regroup the data into target buckets for later DMA write-back. The OCS RMA kernel is widely used in our implementation. This includes message generation during edge processing, message forwarding in global messaging required by the L2L subgraph, and two-stage sorting, which is responsible for all destination L vertices updating. There are some other auxiliary designs and implementation details, such as an in-place global sort based on parallel sort by regular sampling, and Paradis, which is a multi-thread in-place radix sort algorithm. The delayed reduction of delegates parent array, which can eliminate per iteration parents reduction and replace them with one-time communication at the end of BFS run. and deployed and we also deployed edge-aware vertex cut load balancing strategy in edge-to-edge push, which is of low overhead and greatly helps CPE load balance. It's finally the evaluation time. Firstly, let's take a look at the weak scalability. At full scale, we observe 52% of relative parallel efficiency when compared to the single supernode run, indicating good weak scalability. To see what happens in the new partitioning method, we recorded the distribution of subgraph sizes on each node with 281 trillion edges at full scale. The figures shown are the cumulative distribution functions. Notice that x-axis are all in a small range, which indicates that outliers does not occur. To be accurate, EH2EH has a min-max difference less than 4.2%, and the others no more than 0.36%. Such a balanced graph size distribution ensures load balance in the first place. Then it comes to the time breakdown for other techniques. Here we skipped OCS RMA since it's too fundamental so that we cannot finish our implementation without it. The first one, sub-iteration direction optimization, turns top-down sub-iterations into bottom-up. We see that push time is greatly reduced, replaced by only slightly increase in pull mode. Later, we apply CG-aware core subgraph segmenting. Recall that it's an optimization on EH2EH pull. We improved it by 9 times here and get notable improvement end-to-end. Evaluating OCS RMA kernel alone, we tested it in a micro benchmark which bucketized 4 GB uniformly random 64-bit integers by lower 8 bits. Let's simulate multiple patterns we use it in the BFS implementation. The throughput of MPE sequential bucket sort OCS RMA on single CG and 6 CGs are listed in the figure, and we observe that in the 6 CG version, it achieves nearly 5 times throughput than 1 CG, indicating 78.1% efficiency. Speaking to the memory bandwidth utilization, OCS RMA with 6 CGs achieves about 117.2 gigabytes per second, which is 47% of the measured peak. To give a sense on it, in our previous generation OCS, we achieved only 33.7% utilization. The RMA helps us utilize the cores better with its ability to communicate between arbitrary two CPEs in the same CG. And that's all. Thank you.